And what I mean by that is frequently, if you're trying to integrate a product, like we have here in our next example, it will be a good technique, especially if one of your factors is a power of x. It's going to be very helpful.
Well, the voodoo will be helpful?
Yes, the voodoo will be very helpful when you have a product and one of the factors is a power of x. So up here, what we noticed is that we did have a power of x here. It's like x to the 1 multiplied by this fraction. And one of the patterns that you're going to notice is that if you put your power of x with u, you then differentiate the u so the power goes down. And so that's one cue to be aware of. If we put our power of x with u, we have to differentiate it to get to du, which is going to make that power get smaller. Whereas if you put the power of u with the dv, you have to integrate. And so if you had a power of x here, you integrate. That a lot of times is going to make things more complicated because the power is going to go up. Now, of course, there's one-off situations where, you aren't going to put the power of x with u. For example, right here, we have two choices. When we look and we build our little integration by parts table, our voodoo table here, the idea is that we are separating the entire inside into a u part and a dv part. The dx piece always goes with the dv because that's the only way we could integrate here. So we always know the dx is going to go here. And then when we're looking at this, I am seeing two functions, x squared and natural log of x. So one of them is going to go with the u, one of them is going to go with the dv. And what I said on Tuesday, I think that the best guiding principle to start is to pick the most complicated or the biggest piece of the integrand that's easily integrable to put here. Because to get to v, in order for us to get to v, we need to integrate both sides of this. In order to get to du, we differentiate both sides of that u. And differentiation's easy. We can differentiate anything if we know our rules. Integration, though, we can't integrate everything. So when we look at these two functions, we have x squared and natural log of x. We could do this because this will differentiate, making the power go down, so that seems like a good thing. But then over here, we would have to integrate natural log. Do we know an antiderivative for natural log? Do we know a function that has a derivative equal to ln of x? And again, this is one of those tricky things. We can differentiate anything, but only some functions we can integrate. And the only way we get sort of familiar with what we can integrate and what we can't is by doing a bazillion problems. And so when you think about this, you know how to differentiate it for sure. Right? You differentiate, get 1 over x. But we don't know the antiderivative for that yet. Right? That's one of the things you've all been dying to know. What is the antiderivative of natural log? We know its derivative, but we don't know its integral. So that is not a candidate because we don't know the antiderivative for natural log. So this is one of those cases where we are, in fact, going to put the power of x over here with the u's, and we'll put the other function, oh my gosh. So this is one of those examples where we will put the power of x's over here, which when we integrate is going to increase the powers of x, which initially we should be wary of. And we're going to have to think, wow, is that really going to work? And it's going to work in this case because when we differentiate u, we get 1 over x. Don't forget the dx. And when we integrate here, we get x cubed over 3. All right, so there's our formula table for integration by parts. Now we just have to fill in. So now we have to remember our formula. So it's uv minus the integral of v du. So uv ultraviolet minus the integral of voodoo. So there's our formula. Now we're just going to fill in the blanks. So u times v, uv is this main diagonal right there, uv. We usually put the polynomial part out in front. So I'll write this as 1/3 x cubed multiplied by natural log of x. We usually put the log last because you want to make sure that it doesn't look like something's inside the log that isn't. And it's a little easier if you put log last. So there's our ultraviolet, uv minus the integral of v to u. And the voodoo part is the bottom row. It's always down here. So v du. So uv minus the integral of v du. So we're going to integrate v multiplied by du. So we have x cubed over 3. That's our v. And then 1 over x dx. And here, let's simplify this integral a little first before we ask our question. So this is our crossroads right here. This is where we ask ourselves, is this integral easier than the one that came before? So here's the original. And then this is where we sort of decide whether we picked the right combination of functions here or not. We look here. Is that integral easier than this integral? Heck yeah, there's no log in it. That's just a power rule integral. So we've made the right decision. And so then we carry on our merry way. This integrates easily with the power rule. We get x cubed over 3, so we end up with a 1/9 in front and an x cubed, and then a plus c. And now we've integrated that product. So quite frequently, integration by parts works really well when we have a product. And you can imagine all sorts of products that we've seen that this could work for. You'll see a lot of them in the homework. So any questions on the steps? Funny as it may be, what we are going to see next is that we can use integration by parts even when we don't have a product. So this is going to be interesting. We've got these functions like arcsine, natural log, arctangent, functions that you can easily differentiate, but you've never been asked to integrate. You can differentiate arcsine, you can differentiate arctangent, you can differentiate log, but we've never asked how do we integrate these. And this is going to be kind of curious that integration by parts is going to be the key. So when we create our integration by parts table, we have to identify u and dv. Bless you. U and dv. So the top row, the way I do this integration by parts table, I'm taking the inside of this integral, including the dx, and it's got to be separated into a udv. Well, there's not a lot of choice here. There's only one function, right? One function only. The only function is this. The dx has to go over here with the dv, so you can integrate. There's only one function here. If we put that one function with the dv, we're back to the same place that we are. We would have to integrate it. We don't know how to integrate it. So this one really has no choice. The dv has to just be the dx, and the function has to go over here because we know how to differentiate it. We just don't know how to integrate it. That's what we're trying to do, is figure out what the integral of it is. So this is determined for us already. We really don't have a choice in this case because there's only one function. Everybody with me on that? If we put the arcsine with the dv to get to v, we would have to integrate it, but we don't know the integral of it. So we would be back at the starting block. All right, now we differentiate the u to get the du. So the derivative of arcsine, and there's going to be a dx there. So this is going to be, anyone remember the derivative?
Like 1 over rad 1 minus x squared.
Oh, good. Yeah, exactly. That's going to be our derivative. And over here, pretty easy integral. We integrate both sides. We have a differential on both sides. We get v equals x. And remember that typically when you do an indefinite integral, you would have a constant of integration. But we are choosing, you can go through a bunch of examples if you want. It doesn't matter what constant you pick, it would work. If you pick x plus pi or x plus 20 or whatever, x plus 0 is the easiest. So we always choose in practice a constant of integration that's 0. So we just need the simplest antiderivative here. So now we go to our formula, our ultraviolet voodoo. So if we set up the table the same way every time, then ultraviolet is right there. It's the diagonal. So we are going to have x multiplied by inverse sine of x. There's our ultraviolet. That's UV. Minus the integral of voodoo. And voodoo is always going to be this bottom row right there. V du. So if you do it the same way every time, you're going to get some good muscle memory on how this all fits together. And our voodoo includes the dx right there. And that's where we're at. And now, typically, this is where we ask ourselves, did we make the right choice? Well, we had no choice, so we don't really have to ask that question. This integral is easier because it is integrable using what technique? U sub. So whenever we do a U substitution, we are looking inside a square root, inside an exponent, inside an angle. And we see that inside this square root is a quadratic. And its derivative, or at least a multiple of its derivative, is present. Right? The derivative of that quadratic is linear. In the numerator, we have a linear. So it's not exactly it, but it's, it's a multiple of it. So that's fine. Now, when you're looking at the help me solve this stuff in this homework, a lot of times what my math lab is going to do is try to force the derivative of your u to be present, which is fine. You could do that. You could say, oh, the derivative of this is negative 2x, so I want to make this negative 2x, but then I have to divide by negative 2 on the outside. And there's many times where that's pretty easy to do in many cases. But sometimes that process is way more work than is necessary. It doesn't give you a big bang for that buck. We can just do it straight up the way I'm going to do it here and not try to force this to match. When we're doing log form, we have to force that match so that we can do the integral of the absolute value of the denominator. But if it's not a log form that we're trying to target, trying to force your du to match up there it's not always that important. So this is a new u. We've already done our integration by parts u, so now we're doing regular u substitution. So with regular u substitution, we get to this. And here, if we divide both sides by negative 2, that's going to match our x dx, which we see up there. So this is all going to become, we have our x inverse sine of x out in front, minus integral. This is inside the square root, so that's going to be a square root of u in the denominator. And then x dx, right there, that x dx is going to be equal to du divided by negative 2. So x dx, right there, du over negative 2. So du over negative 2. We have a couple of choices. We're pretty comfortable, I would think, by now at realizing that constants can factor out of integrals. So the over negative 2, you can put that over negative 2 out in front, because constants can be factored in or out of integrals and derivatives and limits. Constants can move in between. So there is our new setup. And we'll just do a quick rewrite. So that's going to be plus 1/2 integral. And we'll make that u to the negative 1/2 so that we can integrate it with the power rule. And we will have, so we're going to add 1 to the exponent and get u to the 1/2. Divide by the new exponent. So we divide by 1/2 or multiply by 2, however you want to write it, plus c. And these halves are going to cancel. One's in the numerator, one's in the denominator. And then our final step is the back substitution step. So we go back to this u, our integration by substitution u. So we'll get the square root of 1 minus x to the 2. And that is our antiderivative. So that function, it may not look like it, but if you take the derivative of that function, you will get inverse sine of x. So that'd be a good practice. Take the derivative of that, and you'll end up with arc sine. All right, so let's try this one. This is very similar. There's only one function in here. And we're going to separate the integrand into u and dv. Where does the natural log have to go?
U.
Has to go with u. We can't put it with dv because that would entail an integration, which we don't know how to do. So go ahead and see if you can figure it out. So let u be your natural log and see if you can figure out what the antiderivative for natural log of x is. See if you can start committing that formula, the ultraviolet voodoo formula, to memory. uv minus the integral of v du. Does that mean you're next?
I think Mom gave it to her. My
Oh.
dad, so.
Okay.
First.
Oh, good job.
Yeah.
Right.
Usually patient 0.
Patient 0. Yeah, there's some freaky bugs. We got norovirus over the break, which is horrible. Projectile vomiting. And then it went through our whole house. It was only 48 hours, and then it was like, oh, back to normal. So when we do this one, we take the derivative to get du. Derivative of natural log of x is 1 over x dx. And then the integration here is pretty easy, right? You just get v equals x. Okay. So that's our integration by parts formula there, our table, integration by parts table. So now we do uv minus integral v du, ultraviolet voodoo. So uv, once again, it's always the diagonal right here, uv. So x ln x, x ln x, uv, minus the integral of v du. So there's v, there's du. Oh, we get some cancellation there. So we have x ln x minus the integral of dx. Right, x over x is 1. And what's the integral of dx? X. 1x. So this is our antiderivative. Plus c. So that function, if you differentiate it, you will get natural log of x. X ln x minus x. That is the antiderivative for natural log of x. X ln x minus x. So differentiating that will get us back to natural log of x. Again, a good practice problem that if you do differentiate that you get the right thing. Any questions on any of the steps for either of those? Good. All right, so let's move on to another integration by parts. So here's a product. And another flavor of integration by parts is when you need to use it more than once in a problem. So repeated integration by parts. Anything worth doing is worth overdoing. So, so let's try. So let's first identify a pattern here. We see that there are two functions. So we have a product, which is a classic integration by parts problem, integrating a product. And we see a power of x. And we've had a couple of problems where we've seen the power of x go in different places. Typically, you like to have the power of x be with the u because you differentiate and it gets easier. But we actually did see an example already where if we had a natural log, we had to put the natural log with the u because you could differentiate it and not integrate it. So when we look at these two functions, natural log squared of x, we don't know how to integrate that. And we know how to integrate just natural log of x at this point. But even when you know how to integrate natural log, still putting x ln x minus x for your antiderivative is a little complicated. We still can't integrate natural log squared, though. So this is another one of those cases where we're going to take our power of x and actually put it with the dv. So we have our u, we have our dv, and we need to separate the entire integrand, including the dx, into this top row. So I'm going to let u be natural log squared of x, and then dv be x squared dx. The dx always goes with the dv. Now let's integrate this first. This step's easier. So we get x cubed over 3 plus 0. Pick a constant of integration of 0. All right, now we have to be able to differentiate that log thing. This is semi-new notation for powers of logs. If we have natural log squared x, what that means is that. It means natural log of x squared. It's using trigonometric power notation for log, which it's only a newer thing. A lot of books you look at would always write it like that and not use this new shorthand notation. It's easier to differentiate it here because it's obvious that natural log of x is the base. And usually in this form, you're going to make less mistakes. We see that on the outside is the power, so the 2 comes down, and then we have natural log x to the 1. We subtract 1 from the power. Everyone okay with that? But then we have the chain rule part. So we brought the power down, we subtracted 1, we left the base alone, but now we have to differentiate the base. So the base has a derivative of 1 divided by x. So that's going to be our derivative. So let's write that over in our little integration by parts recipe area here, getting all our ingredients ready. So we have 2 natural log of x divided by x, and then a dx. So now we have all the ingredients. Now we're ready to do our ultraviolet voodoo. So we come up, uv minus integral of v du. Ultraviolet's always this main diagonal. So we'll have 1/3, we'll have an x cubed, and then we'll have a natural log squared of x. uv minus the integral. Voodoo is always the bottom row. And I see a 2/3. I see an x cubed divided by x, so that's x squared. And then I see a natural log of x. And then we have a dx. And here's where we ask the question. Again, we didn't really have a choice in this case, but still we should always at least consider this integral and compare it to the first. We see it's easier because the power on the natural log went down by 1, so it got a little easier. But we still have a product. So that's a clue that do it again, because we still have a product. So we're going to do it again. So we're going to set up another integration by parts. And one thing that is important is that if you do have to use repeated integration by parts, you want to use the same pattern that you used in the first one. If you reverse the pattern, you'll just undo what you already did. You'll be back to the beginning. So we want to keep with the same pattern. In other words, we want to stick with the u being a natural log, and we want to stick with the dv being a power. Now, here, most students have the instinct to see the constant, 2/3, pull it out. That's fine. It's true. You can factor it out. That's totally fine. But notice this whole integral is going to be rewritten as a uv minus integral of v du. So if you pull out that 2/3, you're going to have to put these huge brackets, and that 2/3 is going to have to factor across, or distribute across, I should say. So there's no advantage to, if you factor out that 2/3, you're just going to have to distribute it back in a minute. So this is a pro tip. Pro tip, leave the constant inside the integral. And better yet, we're going to be extra pro tipping. This minus sign has the same dilemma. We're going to convert the integral here to this piece, uv minus integral of v du. That minus would also have to be distributed. If you want to be really proactive, you can push the minus sign in, and then you don't have to deal with brackets or big parentheses at all. If you can push that minus sign in and have that be a plus, then we don't have any distribution to do whatsoever in our next step. Will it work? Of course, you can put your big brackets and distribute the minus, or distribute the minus 2/3. Absolutely. But if you, as you play around with this, you start to see that this little trick of, okay, let's leave the coefficient out here as a +1, it will be easier. So we let u be the natural log piece, and then we're going to let dv be everything left over. So 2/3 x squared dx. Once again, the derivative here is 1/x dx. Integral here, we're just going to use the power rule. So we get x cubed over 3, which is going to be -2/9 x cubed. So there's our recipe. We got all the parts. So I think we can squeeze one more in over here. Let's just move this up a little bit and get it out of the way. Okay, so we've got this coefficient, or not coefficient, this leading term, natural log squared of x, plus. So we converted that minus to a plus and pushed the minus inside, so plus. Now we're back to here. Now we stick our ultraviolet voodoo right there. And because we moved the minus in and this is plus, we don't have to put any brackets to distribute that minus. Our ultraviolet is right here. Okay? So it's this main diagonal. Ooh, that becomes negative. So I'm not subtracting. I'm just putting this in, and this is a minus. So that's just this term. So -2/9 x cubed times natural log of x. So there's uv. minus the integral of v du. So now we look at the bottom row, v du, right down there, voodoo. So we have negative 2/9. So let's just put it inside here. We'll distribute the minus in a second. So negative 2/9. X cubed divided by x is x squared dx. And that's where we ask that question, is this integral easier than what came before it? And of course it is. Now there's no logs in it. It's way easier. So our final answer then, all we have to do is that integration. And if you look at these terms, you start to see a pattern. You see that we've got this x cubed coming along, and the power of natural log is going down until here, where we're going to have no natural log left. So this is going to be plus 2 divided by, power rule, x cubed over 3, so that's going to be a 27 down there, and that's going to be an x cubed, and then we have our constant of integration. So that will be our final answer. Yeah?
Is there ever a time you gotta simplify the UV in the front, or can you always just leave it as that?
The UV, sometimes you'll have some sort of cancellation in here. It's possible. All the ones we've seen so far, we've never had cancellation here, but it's possible. Most of the time, your cancellation is going to be with the voodoo part down here, where you have x's divided by x's, and you can simplify it. It's usually the case.
Whenever you integrate dv into v,
Yep.
you mentioned how you just choose any constant and usually it's 0. Is there ever going to be a time where it'd be more
0 is always best.
0 is always best?
Yeah, 0 is
there
always
ever going to be a
best.
time where if you choose another constant, it,
0, this is one of those cases where we can say it's always best to pick 0. Yeah. Yeah. That's a good question, because a lot of times there are special cases. This is one where I've never seen one. So
yeah,
I
I
always
was
pick
thinking like,
0.
what if there was a constant and if you use the constant and it could possibly
Right.
help cancel things out?
So think about this. So if you do have a constant here, then you're going to end up having to distribute this function across it.
Mhm.
So it's just going to make your voodoo part more complicated because you're increasing the number of terms and you would have to do more distribution. So with the 0, you're going to minimize the number of terms that are here. So that'd be a good exercise to try to find one. See if you could create one where there might be some odd special case that I've never seen. It's possible. Okay, here's another one. We sort of might be getting into this habit of saying, oh, the power of x actually feels like it should be going with the dv all the time. Well, let's take a look at this one. So once again, we see two functions. So in our mind, we're thinking, okay, the x squared and the e to the 4x, one's going to go with u, one's going to go with dv. We have those two choices. Now in practice, there are really just two choices here. But you could be, a contrarian and say, oh, well, couldn't I put x with one and x e to the 4x with the other? Yes, you could. You could break this apart and say, oh, there's more than two choices. That's very rare that breaking one apart and grouping it with the other, very rare that would actually help. So usually if you see kind of two functions jumping out at you, it's going to be one or the other, almost always. So when we start to build our little ingredient table here, we've got our u, we've got our dv, and we know dx has to go here. Let's think about this for a minute. So the reason that the power of x worked over here was that when we took its integral, or found the antiderivative, it did get worse, but it was offset because we ended up with a division by x over here. Right? That division by x took away one of those powers. We just added one here, but then we took it away. That's not the case here. So notice that if we were to put the x squared there and the e to the 4x here, this would get worse And there's not going to be any compensation for it getting worse because the derivative of an exponential is itself. There's no division by x. It would just get worse. So this is the more classic case where the powers of x, stick them with u, because when you differentiate, it gets easier. The power goes down. So that's the more classic. In many cases, when you have powers of x, you want the power of x to go with u, so when you differentiate it, it gets less. The one exception is if you have logs in there, because the derivative of a log divides by x, and that will offset it. Most of the time, powers of x are going to go with u. And then we have our e to the 4x here. The integral of e to the 4x is itself divided by the derivative of the exponent. Now we've got our recipe. All our ingredients are ready to roll. uv is the main diagonal. So 1/4. I'm going to write it in this order. Any order is fine. It's commutative law of multiplication. Typically, we put the polynomial piece in front. Doesn't have to be that way. So uv minus, so uv is always there. And then the bottom row is our voodoo. So uv minus the integral of v to u. So minus integral v, we have e to the 4x over 2, over 4, multiplied by 2x dx. All right, let's think about this. When we look at this integrand versus that one, this one is now easier because the power of x went from a 2 down to a 1. So the power of x, we still have the exponential, that's equally difficult, but then the power of x went down, so that makes the overall integral easier. But we do notice that we still have a product. And we're going to have to integrate by parts one more time to ratchet this down to a 0, from 1 to a 0. And here's that case that I mentioned last time. Your instinct might be to pull the constants all out in front, but the integral part is going to turn into a uv minus integral of v to u. And so if you have anything out here, that's going to then have to distribute across. So it's advantageous to not pull out that constant. And the most advantageous thing to do is actually to pull this in and make that plus and move that minus sign in. And it looks like we're going to have minus 1/2. 2 over 4 is 1/2, plus the minus is in there. And then we're going to have an x e to the 4x if I write it in the traditional order. You have that. And when we're looking at this, we should be seeing two functions. We see that function and we see that function. And yes, if you're thinking in your mind, well, couldn't we put the half with the e to the x? Yes, of course you could. You could change the order. There's no need, though. We have 3 factors being multiplied together. You could group them in any way you wanted. It's just easiest to leave the constant with whatever's in front there. So if you happen to put your e to the x in front of the x, your e to the 4x, you could group the constant with the e to the 4x. Totally fine. It's not going to matter. All right, so let's do our second integration by parts. So we're going to have u in dv. And again, use the same logic. If you put powers of x with u here, put powers of x with the u there. If you reverse your logic, you're just going to undo what you already did. So we want to then put the minus 1/2 x here, and then the e to the 4x dx over there. So then the derivative of u is going to be minus 1/2 dx. And the integral of dv is v, and we end up with an e to the 4x divided by 4. And now we're ready to do the ultraviolet voodoo part. So let's come over here. So we're going to have 1/4 x squared e to the 4x. That's the leading function. Okay. So uv, main diagonal, right there. That's going to be negative 1/2 times 1/4, so that's negative 1/8 x e to the 4x. So there's our uv right there. uv minus the integral of v to u. So minus the integral of v to u. There's v times du. As you do more and more of these, you see, oh, it's negative. You can just pop it out in front and change that sign. I won't do that quite yet, just to make sure that you're seeing where all the pieces are coming from, where all the parts are coming from. So we have that. So then our next line, this function carries down, this function carries down. Actually, I might be able to just, I think this actually works pretty well if we copy. And if I hit here, it's not going to want to paste, is it? Do I have to hold it? How do I get it to paste?
You drag it after you copy it, and then just put it right on top.
So do that, hit copy, and then drag it?
Yeah.
Oh,
Oh.
thank you.
No.
Oh, it vanished. There is a way, right? There is a way. Copy.
Maybe if you paste and then drag whatever you pasted.
But now, but how do I make
Click on
it?
again and paste.
Do I just have to hold it for like 10 seconds before it right clicks? Okay. Not happening. Not happening. I gotta figure that out. Okay, so then over here, let's simplify this before we do our antiderivative, just to make sure you're seeing it. This is going to be plus 1/8 integral e to the 4x dx. Right, the constants can all be factored out at this point. And then our final answer, we'll have all this stuff out in front. And then our final term will be plus 1/32 e to the 4x plus integration constant. And there we go. That will be antiderivative. So when this power on x was 2, we did 2 integration by parts. How many integration by parts would we do if the power were 3? How many would we do if the power were 4? Oh, there must be a formula for a generalization of this. And the answer is yes. It is called the tabular method, which used to be taught all the time in Calc 2, the tabular method. These days, we don't really teach the tabular method, but just allude to it. And if you look in the textbook, the e-text, or if you just did a Google search for tabular method for integration by parts, you'll see kind of a shortcut where instead of recreating integration by parts tables again and again and again, there's one way to use just a big long table and take derivatives of one column and take integrals of the other. So if you're curious about doing integration by parts like 5 times in one problem, look up the tabular method in your free time, and you will find it. We will just do it no more than twice. We'll do it no more than twice. So no tabular methods, unless you're really curious. So any question on any of the steps there? Starting to feel the voodoo? Feel the voodoo? Okay. Let's see. Can I trust you with this first one already? I think I can. So you all tried this one. So there's only one function, but it's a log function. So stick that log with the u. And then your dv would just be dx. So let's see if you can pull the rabbit out of the hat. Tips are free. Oh. Yeah, that's just natural log of 2e. You could do a clever separation like this. If you have natural log of 2e, you could use a log property to write that as log 2 plus log e. Yeah. So you could turn that into, that simplification is possible. What do you all get when you took the derivative of natural log of 2x? 1 over x?
Because that's a composition, right?
Because there's, so normally, you do need chain rule, right? So the derivative of a log is 1 over the inside. But then you have to multiply by the inside, and the inside's derivative is 2, so then those cancel. So you end up with 1 over x. So observation. So if you're taking the derivative of natural log of nx, the derivative would still be just 1 over x. And then we're letting dv be dx, so the integral will give v equals x. So the one piece that's going to be a little different here that we haven't done yet is the definite integral part. And that definite integral part, we have a couple of ways to handle it. So we certainly are going to start out with our regular uv minus integral of v to u, so our regular ultraviolet UV. So there's uv, and here's the one change. This needs to be evaluated on the interval 1 to e. Now it is possible to delay and just do all your evaluation, your fundamental theorem of calculus stuff, all at the end. But technically, we do want to have that notation in there. So uv minus the integral from 1 to e. So uv minus integral, bottom row. Oh, what does the bottom row become? Just dx, yeah. So then, if we didn't want to do the evaluation in 2 pieces, you could just leave this. Don't do it yet. When we integrate this, we get minus x, and then we could do this and evaluate the whole antiderivative at one time. So the integral of dx is x. This would have to be evaluated 1 to e. This has to be evaluated 1 to e, so we can just evaluate the whole thing 1 to e at the same time. Now with this integration notation here, it might be clearer if we put this thing in parentheses, but we just don't do it. So I won't do it. This just means everything in front of it gets evaluated at e, evaluated at 1, and subtract the 2. So any questions getting to this stage? Okay, so plugging in e. So that's going to be e natural log of 2e minus e. So antiderivative at e minus antiderivative at 1. So we're going to plug in the 1 and then take negative 1 and multiply it across. So this is going to be negative natural log of 2 plus 1. Because that minus has to be distributed across. Okay, so that's where we're at. Totally fine to leave your answer like that. If you're over-ambitious, some of you are. Not all of you, I know, but some of you. You could rewrite this as natural log of 2 plus natural log of e. So using a log property, you could do that. And then what is natural log of e? 1. So then you could distribute this e. So e minus e. So you would have your e's canceling, and you would end up with e ln 2 minus ln 2 plus 1. If you want. This is totally fine right there. You can get silly with these log properties. Because couldn't we do another log property here? Yes. If you wanted to say, hey, well, let's just fly this coefficient up here, you could do that. Right? That's a log property. And now you have another subtraction of logs, so you could say, oh, well, then we could combine these two, and it gets to be, kind of tedious and unnecessary. Right? You could do that. Well, then these can be simplified, right? That can be simplified. That's natural log of 2 to the e minus 1 plus 1. Right? So, I mean, it gets to the point. So this would be, probably for the real sticklers on the simplest possible answer, would probably be that. But this answer right here is completely sufficient for us right here. Completely sufficient. It sounds redundant. It's completely sufficient. It's not a bad idea to practice your log properties, though, because there are places where we do need to use them. So having them at your disposal is a good thing.
Which property is that last one you used to get the e minus 1?
This is algebra, where we have a division of exponentials with the same base. So exponentials with the same base, we do the upper exponent minus the lower exponent.
Okay.
You seeing it? So if we look at a simpler case, if we have 4 to the 3 over 4 to the 2, it's a little more obvious.
Okay, yeah.
Right? But if you throw in some letters and, makes it look worse than it is. But this exponent is 1, so this is 4 to the e minus 1.
Cool.
Yeah, make sense? So, yeah, log properties. Okay, let's try another one here. This one is a product, so this is sort of classic integration by parts. We see two functions. Inverse tangent is a function that we do not know how to integrate yet. We know how to differentiate it, but we don't know how to integrate it. So if we are going to use integration by parts, we are going to do integration by parts with the arctangent being part of the u. And then dv will be y dy. Okay, so that's the only choice that makes sense, because putting the arctangent with the dy, we don't know how to integrate it, so let's put it with the u. So then du. I want you to write down du before I write it on the board. Write down du. And if you make a mistake, there's going to be a penalty. We will have to stop the recording. We'll have to close the doors. We'll have to turn off the lights. And what happens in B1317 stays in B1317. But I believe in you. I know you can differentiate. I believe. Hopefully it's not misguided. Don't let me down. One important piece to a derivative, you have to remember the chain rule. Do not forget the chain rule. All right, so first scaffolded piece, I'm just going to put over here the derivative of the most simple arctan function, 1 over 1 plus x squared. Or x squared plus 1, however you want to write it. Okay, so here is the derivative of arctan. So the pattern that we get from here is 1 over 1 plus the inside squared. That's the pattern. 1 over 1 plus the inside squared. So 1 over 1 plus the inside squared. All right, you all got that, thank goodness. Don't have to turn off the lights and close the doors. Multiplied by the derivative of the inside, which is 2y. And then we have our dy, not a dx, because we're using y's. So that is our derivative. If we blow the derivative, the rest of our, we're going to be like in a bad way with our voodoo. We're going to be, haunted. It's going to be ugly. All right, very scary. So uv. So uv, actually, let's just do the whole thing down here. I'm going to call this integral just I, just for the heck of it, so I can come down here and say I is equal to uv. So uv is 1/2 y squared inverse tangent of y squared. This is a definite integral, so we need to put limits of integration up here. We don't have to evaluate right now, though. Let's just leave them there. So everybody agreed that's our ultraviolet? Ultraviolet. Ultraviolet, main row, main diagonal right there. So uv minus the integral of v to u, the voodoo part. So minus the integral, limits of integration will be the same. So minus integral of voodoo. So when we do the voodoo, do we see that the 2's cancel? Right, there's a v du, there's a 2 in the top, a 2 in the bottom, those cancel. So we're going to end up with y cubed divided by 1 plus 1 plus y to the 4th. dy. Everyone okay with that? Everyone see that this 2 and this 2 cancel? Because we're multiplying, one's in top, one's in bottom. Okay. That is integrable using u sub. We'll always look inside, and when we look inside, what I mean by inside here is inside the denominator. The derivative of that quartic is a cubic, which is in the numerator, so it's going to work out great. What form? Log form.
Yeah.
All right. So this is one of those cases where we get payback if we match the derivative up here, because then it's in log form. So we're going to multiply by 4 here, which means multiply by 1/4 on the outside. So now it's in log form, and we can just cut to the chase. We don't have to do a u substitution. And again, out here, let's not evaluate yet. Let's just do all the evaluation all at once. So we can take away this evaluation symbol. We're going to have minus 1/4 natural log, absolute value of the denominator. Don't really need the absolute value bars because that's always positive. And then we have an integration evaluation symbol, 0 to 1 over root 2. So, first let's just observe that if we plug in 0, we get nothing. Let's just get that off the table. If we plug in a 0, arctan of 0 is 0, 0 squared 0, so that's 0. Natural log of 1 plus 0 is natural log of 1, which is also 0. So we can ignore this thing. It's not going to contribute anything other than 0. So we really just have to focus on that. Okay. 1 over root 2 put in here for y, we square it and we get 1/2. So that's going to be 1/4 inverse tangent of 1/2, because we're squaring the 1 over root 2, minus 1/4 natural log. That's going to be 1 over root 2 multiplied by itself 4 times, so that's going to end up being 1/4. So natural log of 1 plus 1/4. We should simplify that fraction. Arctan of 1/2, there's nothing we can do with that. We don't know an angle that has a tangent value of 1/2. If it was inverse sine or inverse cosine, yeah, we could simplify that because we know places on the unit circle where the sine is 1/2 or the cosine is 1/2, but not where tangent's 1/2. The only arctan thing we usually simplify is arctan of 1. Arctan of 1 is the angle that has a tangent of 1, which is pi/4. So then minus 1/4 natural log of 5/4. So there is our exact answer. So it's exact. We haven't typed into the calculator to get an approximation for arctan or natural log. That is our exact answer. Any steps there you want to ask about? All right, well, let's take our break. Let's take 10. Take 10. You can do no math for 10 minutes, or if you want to do more math, you can ask questions. You can get caffeine. Get whatever you need. Maybe not whatever you need. But... Wait, what? It's very interesting, not just interesting.
Oh, very interesting.
Right?
Oh, yeah.
All right, let's do a very interesting problem.
Oh, boy, no.
All right, so this is integration by parts, but here we're going to find the volume of a solid where we do a revolution around an axis. So this should be very familiar and very interesting because you already know how to do it. All right, so a little bit of a review. We are going to rotate around the y-axis, around that axis right there. And we are going to use cylindrical shells. We have two choices. We could use washers or shells. Washers would be bad because we would have to find the x value here and the x value there. So we'd have to have this weird inverse sine thing, which would be a total disaster. Okay, so we are going to use a vertical integration element at a random x. So that's going to create a cylinder. If your element, your rectangle, is parallel to the axis of rotation, it creates a cylinder. The area of a cylinder, the area of a shell or a cylinder, is the circumference of the base times the height, 2 pi r h. When we look at our picture, the radius is the distance between your rectangle and the axis of rotation. What is that? That is x. The height of your rectangle is the function. The function is sine of x. Okay. So area of a cylinder, 2 pi r h. We have a vertical element, so we know we're integrating with respect to x. All right, the interval that we integrate with is always perpendicular to your rectangle. Now we know that volume is just the integral of that. So volume is the integral of your cross-sectional area. We're going to integrate from 0 to pi. There is a cylinder for all of these x's between 0 and pi. So our cross-section, it's not really a cross-section in the traditional sense. You know, they're like nested cylinders. Cross-sections that are cylinders. Now we have a product, though. We're integrating a product. So we will use integration by parts. So integration by parts. Set up our little set up our ingredients over here. So UDV. So we need to break apart that integrand into two pieces. We've got two functions in here. We've got the x and the sine. So a couple of things, couple of guiding principles. Pick the biggest piece that you can easily integrate and put it with dv. Now sine is more complicated and easily integrable than x, so that guiding principle would put sine over here. Another guiding principle is that if you put the power of x with the u, the power goes down. That would put the x here. Oh, both of those actually can work. So we can put the power of x there. We can put the biggest piece that's easily integrable there. So that's a 2 for 2 there. So let's see if it works. So du will be dx, and v will be neg cosine x. So then we're going to have, and now notice, so this is going to be an example where I wasn't thinking ahead and I factored the constant out. So notice this is how we would deal with that. So we have the 2 pi, but then we're going to have these huge brackets because this whole integral is going to turn into our ultraviolet voodoo. So the ultraviolet voodoo, the UV part is minus x cosine x from 0 to pi. UV minus the integral of voodoo, the bottom row, minus cosine x dx. Close the big brackets. So if you don't put your constant on the inside, then you've got to deal with this distribution later, which we're going to do. So let's not evaluate this yet. Let's do all of the evaluation at the same time. So we're going to leave this here. We know that minus can factor out and turn into plus. Antiderivative for cosine is sine. And then all of this whole antiderivative thing gets evaluated 0 to pi. We've got our huge bracket out there still. Let's try to make them the same size roughly. So then we have 2 pi multiplied by, let's see, plugging in pi. Oh, look at this. What is sine of pi?
0.
Oh. I only have one pen. I can't throw it. I need it. So sine of pi is 0, and also sine of 0 is 0. So this whole term here is just going to contribute nothing, right? Sine of pi is 0, sine of 0 is 0. So we're really focused on this first term. So what is cosine of pi?
0.
What? Oh my God. Killing me. Cosine of pi, we're over here on the unit circle. Negative 1. So we're going to have x minus, now we plug in 0 here. And what's 0 times cosine of 0?
0.
0. Now you can say you're 0 and get away with it. How did that turn into just an x? What's that? That's supposed to be a pi, right?
Yeah.
So pi goes in for x. And then pi goes in here. Cosine of pi is negative 1, so that makes it positive pi. And then we subtract off what we get when we plug in 0. So it's going to be minus and minus, but it doesn't really matter because it's all 0. So here is our volume. 2 pi squared. 2 pi squared. 2 pi squared. Fun and interesting. Fun and interesting. Okay. So integration by parts, now that you have that technique, it can show up in all sorts of weird places where we have other concepts that we're underscoring, like finding volume. There is one variation to integration by parts. This is called integration by parts in this class with a twist. That is not something, if you go look on the internet for integration by parts with a twist, you will probably not find it. But this is how we're going to refer to it. A, because it makes sense, and B, because we need some way to distinguish this type of integration by parts from the other ones that we've seen. So some twisted voodoo is coming your way. Notice that we have a product that we're integrating. There's two functions. And we've done several examples where one of the functions has a repeated derivative, like an exponential, derivative of an exponential is itself. But notice that both of these functions have a circular nature to their derivatives. Derivative of sine is cosine, but then derivative of cosine is back to sine. So there's this circular nature to that derivative and certainly to the exponential derivative. So that's what distinguishes regular integration by parts from our twist piece, our twist part. So let's figure out how to do this, integration by parts with a twist. So when we do integration by parts with a twist, it does not matter which of those functions you put with u or dv. It's not going to matter. So we use this technique when we have two functions that have circular derivatives. Doesn't matter which one you put with dv. So for u, you put whatever one you are not going to make a mistake with the integration. If integrating the exponential is easier for you, then put it there. If integrating the sine 3x is easier, put it there. It's not going to matter. Taking the derivative, hopefully that's not a problem. But you do have to integrate here. So whatever one's harder for you to integrate, put with the derivative. But it doesn't matter. So I'm just going to do it in order since it doesn't matter. I'll just keep this order that they put them in here with. So sine 3x. So then we do our regular stuff. du is going to be negative 2 e to the negative 2x dx. V is going to be negative cosine 3x divided by 3. So antiderivative for sine is minus cosine. And then why is that 3 in the denominator?
Reverse chain rule.
Reverse chain rule. Exactly. Exactly. OK. So let's move that. So now we have, this is uv. So I'm going to write it in sort of the traditional order. Again, order doesn't matter. Multiplication is commutative. So there's uv. That's our ultraviolet. That's the main diagonal right there. Main diagonal is always top left to bottom right. When you get into linear algebra and you have to do things like determinants, that's important to call that the main diagonal. So uv minus the integral of v du. So now we're multiplying these two together. When we multiply these two together, we get positive 2/3. We'll put the exponential next, so e to the negative 2x. Then we'll put the trig function, cosine 3x dx. Everyone okay with that? So bottom row multiplied together, that's our voodoo, VDU. Okay. We have a product again. The difficulty, this is normally where we say, oh, is this integral easier than the other? And the answer is no, it's not easier. But the answer is also no, it's not harder. It's the same. We have a trig func, we have a sine or cosine with e to the x. It hasn't gotten any harder, hasn't gotten any easier. So we're going to keep on going. When we do integration by parts with a twist, we're going to end up with this integral that looks very similar. It's similar in difficulty. And we just keep on going. So we're going to have to do it twice. I'm doing it twice. Here we go. Now, I am paying attention this time, and I know that it's going to be easier with the coefficients. And if I don't want to write the big brackets and distribute the minus, I'll just pull the minus in right away. Again, you don't have to. You can just do what we just did in the last one. The minus can just be outside a big pair of brackets. Doesn't matter. But this will at least make it a little bit easier. So now we are going to go with our second integration by parts. We want to keep the same pattern. If you change your pattern, you're going to undo what you already did. So we're going to let u be the exponential piece. So I'm going to treat this as the first function. This is the second. I'm going to put u equals negative 2/3 e to the negative 2x. And I will choose dv to be cosine 3x dx. Okay, now we have to differentiate. Oh, that didn't go with it, did it? Let me try to grab that again. So the derivative of the exponential part, we're going to get du. We have to take the exponential and rewrite the exponential, but then we have to use the chain rule and multiply by the derivative of the exponents. We have to multiply by a negative 2. So we're going to end up with 4/3 e to the negative 2x dx. And v will be sine 3x over 3. Derivatives and integral, okay? So remember, for an exponential, our rule is that the derivative is itself multiplied by the derivative of the exponent. So now we have our leading function. And now we're going to do our uv minus v du. uv is negative, so we're going to turn that into a negative. uv is negative. So u times v is going to be negative 2/9. If we look at the coefficient, the numbers first. And then we have e to the negative 2x, and our trig function is sine. So there's uv minus integral of voodoo, bottom row. It's positive, so that's cool. So that just stays as 4/9. So constants first, and then we have our trig function, e to the negative 2x, and then our exponential function, and then our trig function. So we've got that. Okay, everyone with me? Does that integral look harder or easier than the original? Same! All right, let's go back to Algebra 1. Algebra 1. We have this integral on both sides of the equation. If I were to give you something where you have the same variable on both sides of the equation, how would you solve that? Move them to one side and combine them, right? You would put terms that are like on the same side, correct? So we move this thing over. And now normally in your mind you'd just be like, oh, 1 minus 4, whoops. 1 minus 5 is negative 4. But if you wanted to get really technical, you could factor the x out, right? And then you would get x equals 2 divided by negative 4, which is negative 1/2. But the process would be combine, put on the same side, and combine. And the combining could be with factoring. All right, that's fine. So we're going to do the same thing. But we're going to need to call this integral something. We don't want to rewrite this thing several times. So we need a name for this integral. So we have to just call this expression something. Usually most books will just call it I. If you want to call it something different, you can. You can call it gamma or zeta or whatever. But where we're at right now is that this whole thing, right? This is the right-hand side. We have this string of equals. So this thing equals that thing. Well, if we call this thing up there I, then we have that. I is equal to that. It's the original integral. And we can rewrite this in a clever way. I'm just going to pop those two things down. Isn't this just minus 4/9 times I? All right. So now we're in that algebra 1 land where we have two terms with the same variable, so like terms. We're going to add this I expression to the left I expression. We're going to think of this as 9/9 I. So if we have 4/9 I added to 9/9 I, we end up with 13/9 I. That's going to equal, all this stuff. And I'm going to change over here and put a plus c. We know that this is an indefinite integral. We know that you have to have a plus c in there. And we've got this integral on the left and this integral on the right. And so when we combine them, we know we need to end up with a plus c. So as soon as we take away the inherent plus c from this side, then we want to put it in here. As soon as we combine those integrals, we want to put a plus c in. So what do you think our very last step is? Multiply by? Our goal is to
Multiply by 9/13.
figure out what I is, right? We want to solve for I. That's what we want to know. If we say I is this indefinite integral, we want to know what's that indefinite integral equal to. Well, I know what 13/9 of it is equal to. So let's get rid of the 9. Let's get rid of the coefficient by multiplying by 9/13. So we're going to come through and multiply by 9/13. So we're going to have minus 9. So if we can cancel the common factors probably in our head. So this is 9/13 being multiplied here. So we're going to end up with 3 over 13 e to the negative 2x cosine 3x. So that's multiplying by 9/13. You can do this if you want also. Just put a 9/13 out there, multiply by the whole equation. So then we multiply 9/13 times this, and we end up with negative 2/13 e to the negative 2x sine 3x. And then we have the 9/13 times a constant. And we treat this constant in calculus like it's a recycle bin. If we multiply a constant by a constant, it's still just a constant. So yes, these two c's are different, but in calculus, we only care about our final c. If somebody said, plug in 0 and figure out what c is, you would do it here, not there. This is the c that you would solve for. So that is our integration by parts with a twist. Right? We're taking this integral and we're twisting it over to that side and combining it. So integration by parts with a twist. We integrate twice, we end up with a like integral, and we move it to the other side. And then divide by the coefficient or multiply by the reciprocal of the coefficient. That's pretty cool that works. So as you can see, when we've got these extra numbers in here, these coefficients, it gets a little bit tedious because you end up with these fractions that are a little bit, kind of unwieldy, or at least you have to be thoughtful. I want you all to try this one where the coefficients are just 1. So we have e to the 1x, cosine of 1x. So it'll be a lot simpler. Not trivial, but a lot simpler. So see if you can do this one. And pick whatever you want for u, whatever you want for dv. There's two functions. You can use either. When it's integration by parts with a twist, doesn't matter. So go ahead and start doing that. excited.
Okay, so is du supposed to be basically the integration of u?
Du is a derivative of u.
Okay.
Yeah, derivative of u. So on the in the left column, we're always differentiating, and in the right column, we're always integrating. So to get to du from u, we derivative, and to get to v from dv, we integrate. So the, let's see, so uv minus integral of vdu, so vdu is negative. Yeah, so then you want to pull it in and make it all positive. Because that minus will combine it and make it positive. Yes. Yeah, exactly, because you're subtracting off this negative. Your VU is negative.
That's fine.
Then we're gonna make that positive, yeah. Now you're,
Right track still.
yep.
Okay.
Now you're flying. Well, now you're just gonna do integration by parts a second time and use the same pattern, like the UV your trig. Nothing happens with this guy. That's just baggage.
Just totally restart.
Yep, restart, just looking at this integral.
So I just do UV minus VD.
Yep, and this is just gonna stay out in front, so it's just coming along for the ride.
So it is.
It's coming down, but it's not part of the integration by parts. Yes.
Plus.
Yep. Correct. Yeah. So yeah, that coefficient function or that leading function just sticks around, but we don't, yeah.
Yeah, that makes it.
And then integral of that thing.
Yeah.
Yeah.
I'm sure this is, I'm getting my I to the original function.
Yep.
But I have the exact original function, so it would just be I minus
So
I.
that can't be true. That something's wrong then. Something's wrong because then you get 0.
I
right?
did that too. Do you know what you can
Oh my
do?
gosh.
What? The derivative of, like, the integral of sine of x is negative cosine x. So it should be like you're subtracting your second integral, which means you'll add a sine.
Yeah, you should be getting 2.
I did the same thing, but you should get 2 on it.
So here, so this is just double check, so UV looks good, minus the integral, so this is going to become a plus. So if you simplify that, that's all a plus, and then that's going to be sine, and that's going to be yeah.
So what does this integral look like? No. It
Do you
looks
care where we put the e to the x?
So we can set this equal.
Does anyone have a particular preference that we should demonstrate?
Rewrite them. If this equals this.
Anyone care? So we'll do the e to the x with the u, dv cosine. Derivative, so I saw a couple of, several papers, make sure you put your dx here. So when we differentiate, it's du dx equals e to the x, or du equals e to the x times dx. So we want to have an x there, dx there. And then a dx up there for cosine, and we end up with sine. Okay, so I'm going to call the original integral I. So I is going to equal ultraviolet voodoo. So e to the x sine x, that's uv, ultraviolet, main diagonal, minus the integral of v du. So v du is going to be e to the x sine x. Yes. And then we're going to do integration by parts again, using the same pattern. So u will be the exponential, and dv is going to be the trig. So what I see up here is I've got this leading minus. I'm going to be clever and say, oh, let's push this to the inside. So then u is going to be negative e to the x, and dv will be sine x dx. So du will be negative e to the x dx, and v will be negative cosine of x. So any questions up to that stage where we've got both integration by parts tables?
Well,
So then this is going to be coefficient function or leading function just stays. And I switch this to plus. And now uv is e to the x cosine x.
Figure out where you're gonna place.
uv minus the integral of the bottom row. Bottom row is e to the x cosine x. Two negatives make a positive. So we have that. And what do we notice about this integral?
Oh, you're right.
It is equal to
You are right.
I. Right? That integral is exactly equal to I. So we have minus I.
So you did good.
Then we do our twist. We're going to do our twist, and we're going to end up with 2I. I and I.
You run this and see.
And as soon as we do our twist, we have to put a C on the right-hand side because it's an indefinite integral. It's a family of antiderivatives.
Don't lose points. Remember that.
And so then our final answer is going to be found by dividing by 2 so that the left-hand side becomes a single I, because that's what we're trying to find. We're trying to find I. Trying to find I. So that's our final answer. That function's derivative will be e to the x cosine x. Paul, you have a question?
No.
You're looking very intently.
I'm just staring.
Staring at math, yeah, it can be debilitating.
Alternatively, could you just write all that over to?
Yes, you could.
Okay.
Yeah, you could. For sure. Yeah.
Would you have to simplify by pulling out an e to the x?
No, and that's because this term does not have an e to the x in it. So if you're going to factor, factoring is desirable if you can factor out of every term. But if this term doesn't have an e to the x in it, it doesn't give us any advantage. So yeah, no need to factor out of just 2 terms. All right, any other questions on integration by parts with a twist?
Could I have made u cosine of x?
Mm-hmm. If you stuck with the same pattern, so if you let u be cosine here, then when you do your second integration by parts, you'd let u be the the sine function. Yep. Yeah, it's not going to matter. When you have the twist, when both of these functions have these derivatives that sort of circle, it's not going to matter which one goes where. You'll end up with the same exact answer in the end. It's not going to matter. So you can, whatever floats your boat. Any other questions on it? Okay. That brings us to probably the easiest section in this unit. Integrating, it sounds more complicated than it is, integrating powers of sines and cosines, but hopefully we'll see that it's not that complicated. So we have 2 rules. If one of the powers is odd, so we're dealing with just sines and cosines with integer powers. So if one of the powers is odd, and by odd we mean in the numerator, like if you have 1 over sine cubed, we're not considering that an odd power because that's really cosecant cubed. So powers of sine and cosine in the numerator. If one of the powers is odd, split off a factor for the differential and convert the leftovers. Okay. If both powers are even, we use power reduction identities. We've already done that. Right? If it's sine squared, we use power reduction. If it's sine to the 4th, you would break it into sine squared times sine squared and power reduce both. So the new thing is if we have an odd power. So it says split off a factor for the differential. So what do I mean by that? Okay, well, we have sine cubed, so we have 3 factors of sine. We're just going to pull one off and toss it to the differential like we're feeding a beast. So we're going to pull off that sine x. Differential is going to gobble it up right there. So we pull one off. All right. So this is the factor that we're splitting off. And then these are the ones that are left over. So we need to convert these leftovers. So these are the ones I'm referring to as leftovers. So we start with 3 factors, we pull one off of the differential, and then we're going to convert whatever was left. And by convert, I mean convert to the co-function. If we have sines, we convert them to cosines. If we had cosines here, we would convert them to sines. All right? And we have a Pythagorean theorem that allows us to convert. Right? If we have sine squared, that's 1 minus cosine squared. If we had cosine squared, that's 1 minus sine squared. So we use the Pythagorean theorem to convert the leftovers. Okay, those guys are left over. We're going to convert them. And now we are ready for u substitution. Remember, we pulled off this factor for the differential. If we let u be cosine, its derivative is right there. All right, so the piece that we pull off is going to be the derivative, or a multiple of the derivative, but a derivative-ish of whatever we convert it over to. All right, so the differential is going to be the derivative of what we're going to let u equal. And u is always going to be the function that we converted over to. All right, so let's try it. So u is going to be cosine x. The derivative of cosine is minus sine x dx. So when we convert and substitute, we have 1 minus u squared. And this is going to be minus du. So I can put the minus out front and put the du at the end. So minus du. So that minus goes over here. We have minus du is sine x dx. Sine x dx is right there. So sine x dx becomes minus du. And that's easily integrable. That's a polynomial. We can use the power rule. So we have this leading minus, which is a little bit of a headache, but that's okay. We could distribute the minus in and make this u squared minus 1. But we'll just leave it out this time. So we integrate 1 and get u, integrate u squared and get u cubed divided by 3, and then plus c. So when we simplify this, we now have to go back. U is cosine, so we're going to get minus cosine x plus 1/3 cosine cubed of x plus c. So odd power, pull one off, convert the leftovers to the co-function. Sine and cosine are co-functions of each other. Okay, let's look at this one. So we have a product of sines and cosines. One of those functions has an odd power. So we're going to pull one off and convert the leftovers. So the sine squared is just sitting there. We're not doing anything with it yet. But the cosines, we're going to pull one off, group it over with the differential. So that we pulled one off. These ones, we are now referring to the ones, these are left behind. These are leftovers. So we pulled one off. Now we've got these leftovers. We need to convert them into what function? Sine. If we're converting cosines, it means convert to sines. If we're converting sines, it means convert to cosines. So we just convert to whatever the other function is, the co-function. All right, so how do we convert cosine to the fourth? So we're using our Pythagorean identity. we know that cosine squared is 1 minus sine squared. So we have 1 minus sine squared, quantity squared. And then we have our differential grouped with the single factor that we pulled off. So the idea is when we have this odd power, we pull one off, which forces the power to be even, and even powers of sine or cosine can be converted with the Pythagorean theorem. Cosine to the fourth is cosine squared squared. Okay? Now we go with u. U is going to be which function?
Sine.
Sine. Its derivative is in the yellow. Right? Whatever we pulled off is going to be the derivative of what we let u equal. So we're going to let u be sine of x. And then du will be cosine of x dx. And I'm sure some of you are thinking, should we FOIL that out? And the answer is yeah, we should FOIL it out. But it's going to be easier to FOIL it out once we convert over to u's. So if we let u be sine, there's a u squared. There's a u squared. And then cosine x dx is right there. Cosine x dx is that. Now we have to do some algebra. We need to FOIL and then distribute the u squared. So this is going to be 1 minus 2u squared plus u to the fourth. Foiling. Then we have one more step there. We have to distribute that u squared. And now we can integrate using the power rule, back substitute, get the signs back into play. So we're going to have u cubed over 3, 2u to the 5 over 5 plus u to the 7 over 7 plus c. And u is equal to sine of x. So now we go back to sine. So our final answer, maybe I'll write it in descending order. You don't have to, but. So I'm just taking u and replacing it with sine x. So then minus 2/5 sine to the 5 of x plus 1/3 sine cubed of x plus c. What questions do we have? Okay, so far? Wait.
I don't know.
Down to here?
Yeah, sorry, I'm still confused as to why you put the 107 at the start there.
I just went in descending order.
Okay.
You don't have to, but usually we write polynomials in descending order, or powers of sine. Any other things that you're... Okay, let's try another one. So the other option, so we're going to look at two types of these products of powers, sines and cosines, tans and secants. And that's because with sines and cosines, we can use a Pythagorean theorem to go back and forth between the two. Same with secants and tangents. Our other Pythagorean identity allows us to go back and forth with secants and tangents. So that Pythagorean identity, remember I showed you this triangle, which I think is really helpful. If you can get this triangle, it's not a rectangle, it's a triangle. If you can get this thing remembered, there's tangent of theta, the hypotenuse is secant of theta, and 1 is the radius of the circle. Okay, So this one's a little more complicated. It says if the power on secant is even, pull secant squared off for the differential and convert the leftovers. So if the power on secant is even, pull 2 off, secant squared. The thinking is that you're going to let u be the other function. If you let u be tangent, the derivative of tangent is
Secant squared.
secant squared. So we're pulling off secant squared so that if we let u be tangent, the derivative of tangent is then over there stuck with the differential, secant squared dx. Okay? Now this one, yes, we have an even power in secant, and we're pulling 2 off, which doesn't really matter because we only have 2. There's no leftovers, right? So this one we can integrate directly. We could say u is tangent. If this was a secant to the 4th, we would have to convert those 2 extra secants to tangents. Okay. But notice the principle. If we're pulling off secant squared so that we can let u be tangent. And then du would be secant squared dx. If we take a quick glance at the second one, if the power on tangent is odd, so we have either secant to even or tangent to odd, we're going to pull off a sectangent. Why would we want to pull off a sectangent? What would we let u equal if we pull a secant and tangent over to the differential?
Secant.
Just secant. Just secant. Remember that if we let u be a power of a trig function, you have a chain rule thing that gets messy. If you did have secant squared, you'd have to let the 2 come down, subtract 1, then you'd need to differentiate secant, get a secant. It'd be a mess. So our 2 u's are either going to be tangent or secant. We let u be tangent if we pull off a secant squared, and we're going to let u be secant if we pull off a sectan. All right? So let's finish this first one up. So we said we pull off secant squared, we group it with the differential, we're going to let u be the other function. We're going to let u be tangent. So let's see how that plays out. So if we let u be tangent here, du is secant squared of x dx. So that tells us that this whole integral can be rewritten as u squared du. See that? So the du is grabbing everything in yellow. And now we can do our regular power rule. We get u cubed over 3 plus c. And then we do our back substitution. And we plug tangent in for the u. So we get tan cubed of x plus c. Okay. Okay, so when secant is even, pull off a pair of secants. Now we're in the second case. Tangent is odd. This says when tangent is odd, pull off a sectan. All right. Do you see a sectan?
Yeah. Oh, not there.
Right? We don't see any secants, do we? Do we agree there's no secant there?
Yeah.
Don't see it.
What do we do in calculus when we want something and it's not there?
Right. Just put it there.
Cry. Wow, weak-minded. Think about your conjuring skills.
Put it on both sides.
So both sides meaning top and bottom. So if we need a secant, we create a secant, but if we create a secant, there's a consequence. So if we create this secant in the numerator, we also have to put 1 in the denominator, because our conjuring power means multiply by 1. We always multiply by 1 if we need something that's not there. So now we can follow the rule. The rule says if the power on tangent is odd, power and tangent is odd, we are going to pull off a secant. All right, so now we have a tangent and a secant we can pull off. If we pull off a tangent, we're left with tangent squared of x. And if we pull off that secant in the numerator, so we're pulling off a secant. So this part, we group that secant with the differential and sort of leave it there, with the intention of letting u be secant, because the derivative of secant is secant times tangent. Oh, but we still have tangents here. So we have that same second part of our thing, of our algorithm. Pull off sectan for the differential and convert the leftovers. So we pulled off this tangent thing. These guys are considered the leftovers. If we're going to let u be secant, we need to have just secants here. So we need to use a Pythagorean theorem to convert those leftovers. So we left two tans behind. We know from our identity that tangent squared is secant squared minus 1. So we have secant squared minus 1 divided by secant multiplied by sectan dx. Now we are ready for u substitution. If we let u be secant, du is right there. It's what we pulled off. So if we let u be secant, then du is secant x tangent x dx. So our integral becomes the integral of u squared minus 1 over u du. So that whole part right there, that is du. And if we let u be secant, we just replace the secants that we see with u's. We have that. And how do we integrate that? There's two ways that we talked about on Tuesday. One way's easier than the other.
Long division.
We could do long division because it's top heavy. That's improper. Or we could split the fraction. We can split the fraction into two. And the long division will actually give us the exact same expression if we just split this. So if we split it, we have that. All right? We take that u and distribute it. We divide it into the u squared, and similarly we divide it into the 1. So we do both. So we split it. Those are easily integrable. So we get a 1/2 u squared minus ln absolute u plus c. And then our final step is that back substitution. So we're going to have 1/2 secant squared of x minus natural log of absolute secant. That will be our answer. So sines and cosines can go back and forth through a Pythagorean theorem. Secants and tangents can go back and forth through a Pythagorean identity. And the idea is whatever we pull off, we're going to let u be the function that has this as its derivative. All right, let's try another one. Okay. This one can be done either way. So our two rules were, if the power on secant is even, pull off a pair of secants. If the power on tangent is odd, pull off a sectan. Here we have an odd power on tangent and an even power on secant. one of them is going to be much easier than the other in the convert the leftovers piece. Let's think about it. If secant is even, we pull 2 off, and how many are we left with then to convert?
2?
2, right? If tangent has an odd power and we pull off sec tan, how many tans are left over? 8. Converting 8 tans, we would have to say tan squared is secant squared minus 1, but then we'd have to raise it to the 4th power and then do a bunch of foiling, superfoiling. So it's going to be most expedient if we do the let's pull off 2 secants. So if we treat the secant as the even that we're going to focus on, then we're going to pull off 2 secants. These secants are left behind. So those ones are the leftovers. Those are the ones that we need to convert, with the goal being let u be tangent, because the derivative of tangent is now with the differential. So our conversion then, we have tangent to the 9th, secant squared. If we look at our identity, secant squared is tan squared plus 1. And then we have secant squared here. And now we are ready for substitution. If we let u be tangent, then du is secant squared of theta d theta. So this whole really complicated looking thing boils down to u to the 9th times u squared plus 1 times du. Then we distribute the u to the 9th, so we have u to the 11 plus u to the 9 du. And then we're going to integrate. So when we integrate this, we're just using the power rule. Nothing special. Add 1 to the exponent, divide by the new exponent. Add 1 to the exponent, divide by the new exponent, plus c. Back substitute to tangent. So we have 1/12 tangent to the 12th of theta, plus 1/10 tangent to the 10th of theta, plus c. Any steps there that seem mysterious? So the nice thing about these powers of products is that it's very algorithmic. You know, with integration by parts, we have to figure out what do we use for u, what do we use for dv. There's a little bit more problem solving there. Here, it's much more algorithmic. If the power is odd on tangent, if the power is even on secant. So as you do a few of these, most people are going to find this stuff a little bit easier than some of the other stuff where there's more ambiguity. All right, when we look at this next one, that is not considered an even power on secant. So we won't, I'm just going to rewrite this one. So this one, the way we want to think about this one is that those secants are in the denominator. We can't pull off 2 secants and group it with the differential with division. So when we say the power on secant is even, we mean in the numerator. When we say the power on tangent is odd, we mean in the numerator. So this one says, if tangent has an odd power, we're going to pull off what? Sec tan, but there is, again, no secant there. So we do have to do one step before we can do what we're told to do, we would have to multiply top and bottom by secant so that we could then factor off a secant. So if you need a function and it's not there, multiply top and bottom by the function you need, and then you're good to go. So we'll finish that one on Tuesday. All right, we'll stop there. Have a good weekend. Do a ton of math. Do a ton of math. I will be out of town this weekend, so I'm not going to be quite as prompt on my email responses, most likely. I will have email. I think they have email in North Carolina. But email me if you have questions. Hit the Ask My Instructor button. Give me something to do while I'm off. Not skiing because I'm on the East Coast.